Hi, we are team 13344, and we are presenting our MathWorks Math Modeling Challenge finalist paper. I'm Alex.
I'm Jack.
I'm Vinay.
I'm Julia.
And I'm Danny.
Okay, now getting into our paper. Our paper addresses the potential impact of electric trucks on the trucking industry. Through several different mathematical models, including a Monte Carlo simulation and a geometric proof, we concluded that electric trucks will have a massively positive economic and environmental impact. Getting into our first model, we were asked to predict the percentage of semi-trucks that will be electric within 5, 10, and 20 years. I'm going to go over a little of the assumptions that went into our thoughts in developing this model. So our first assumption is that the semi-truck market size will stay constant. We developed this assumption by looking at the size of the market over previous years, and although it did vary some from year to year, it seemed to vary almost randomly, so we weren't able to extrapolate any information about the size for previous years, so we just wanted to simplify and assume that it would stay constant in size. And then probably our most important assumption is that consumers will act financially rational. We did this entire problem as an economics problem where each consumer is going to go to the market, and this only makes sense if we assume that a consumer is acting financially rational and not taking other factors such as environmental impact into account. And then one other important assumption that I'm going to go over is that we ignored short haulers in the purchasing data. So we were only looking at the purchases of new trucks, and from what we researched, it seemed like almost all short haulers are just old, long, and regional haulers, meaning that they're not bought new, they're just coming from retired trucks. So therefore, they wouldn't be included in the new market. So coming from these assumptions, I think our model arises pretty naturally. And what it does is it looks at all 1.7 million semi-trucks, of which 850,000 are long haul and 765,000 are currently regional haul. And then it simulates each one as an individual unit. Once one truck is too old to be useful anymore, then the owner of that truck goes to the market and chooses the cheapest option. Now, Jack is going to talk a little more about how we implemented this in a simulation.
So we implemented this simulation as a MATLAB program in which the fleet of trucks in the United States is represented by a large matrix. The columns of this matrix are individual trucks, and the rows represent characteristics of those trucks. So electric versus diesel, long versus regional haul, current age, and finally lifespan. So every year the age is increased on every truck, and when the truck reaches its lifespan, the program will evaluate the cost function and replace it appropriately with either an electric or a diesel truck, with the lifespan and the initial cost of that new truck being random according to a specific distribution. So we ran this simulation for 5, 10, and 20 years, 20 times each, allowing us to get an idea of the spread of this data. So our results are shown in these histograms, and we were able to quantify these results by calculating means and 95% confidence intervals. So for 5 years, we expect about 43% of trucks to be electric. That number goes to 83 in 10 years. And finally, after 20 years, as can be seen in this histogram, all of our simulations resulted in 100% of trucks being electric. And just a note on these confidence intervals, we calculate these using a bootstrapping procedure. So moving on to the strengths and weaknesses of this model, the primary strength is that it simulates trucks on an individual level rather than a macro scale. So that allows us to incorporate the natural variability in the lifespan and cost of each truck. Finally, the weakness is that it doesn't account for non-economic factors. So for example, a company might not want to take the risk of trying something new, or a company might have altruistic environmental concerns that lead them to adopt electric vehicles faster than they would if they were just thinking economically rationally. Moving into section 2, the problem asked us to determine the number of chargers and stations needed on each of 5 trucking corridors, given that all trucks on the road are electric. So we make a couple of assumptions here. First of all, we assume that a lower number of stations is always a preferable configuration. And this is due to the fact that the cost to add chargers to existing stations is much less than the cost to build a new station. Second, we assume equidistant stations, not because this is necessarily the optimal spatial distribution, but because it will yield the same minimum number of stations as the optimal configuration. If we start with equidistant stations, all separated by a distance d, the maximum distance a truck can drive on a single charge, it is impossible to construct a configuration with fewer stations that is viable because there will always be a space greater than d by the pigeonhole principle. So therefore, we can make the assumption that all stations are equidistant. Third, we assume that all trucks entering the route have 80% battery at the least. We assume all trucks are Freightliner e-Cascadia models to simplify our analysis. And finally, we assume that all charging stations use DCFC chargers, which are much more efficient than traditional chargers and, in our opinion, necessary in order to implement electric trucking on a massive scale. The variables we use for this section are S, the number of charging stations along a given route, M, the mile along the route closest to a given charging station, D is the total route length, N is the position of a given charging station, so first, second, third, C is the number of chargers at a station, and finally T is the traffic density on the highway, trucks per mile per day.
So, as Jack said, in developing our model, we assumed that the optimal way to place charging stations is to make them equidistant from each other and from the ends of the route. And based on data on optimal charging techniques from the provided information sheet, we decided to also assume that trucks would use up 60% of their battery before heading to a station to recharge. Because the trucks used in our model can drive 150 miles using that much battery capacity, the optimal number of stations per route is just the total length of the route divided by 150. We then set out to find the amount of chargers required per station. Because of the large distance between stations, each charging station will have to accommodate every truck that passes it in a day, and we can determine the number of chargers needed by the amount of truck traffic each station gets. To define the number of chargers at any given station, we found the average number of trucks that pass each station daily, then factored in average charging time to find the minimum number of chargers that can efficiently accommodate the most trucks. We tested our model by analyzing 5 major US trucking corridors. Longer routes generally had more stations, and because of differences in traffic density, different stations on the same route often had different amounts of chargers. Some stations had as few as 330, while others had over 1,200. This model optimizes stations by placing them only where absolutely necessary to save land and costs, but we recognize that a potential weakness is the large amount of chargers at some stations. So we decided to do some further analysis to find out whether we could feasibly make all our charging stations no bigger than the largest widely used diesel stations with about 120 chargers. We found that for this to happen, each truck would have to charge in a little under 12 minutes. And we interpreted this as less of an indicator of the infeasibility of our model and more of an indicator of the infeasibility of the context of this problem, which is the entire US trucking industry as it is today suddenly switching entirely to electric. However, we also found that the Chanje V8100 battery, which is for a smaller truck and can fully charge in less than an hour, could make this scenario realistic if all trucks used it. So as battery technology improves over time, we believe that this model could become a much more tangible reality. And now Vinay and Dan are going to talk a little about our part 3.
In part 3, we developed a relative score that would show how likely and beneficial the installation of electric trucking infrastructure would be along each of the 5 given trucking corridors. We started with 2 assumptions. First, because state legislatures are the ones that allocate funding towards highway development, data on how beneficial electric trucking can be was taken on a state level, averaging the states that each corridor passes through as a single region. Second, we assumed that polling data reporting negative opinions about an increase in carbon emissions will be predictive of opinions in support for electric trucking infrastructure, because an increase in electric trucking would result in a decrease in carbon emissions. To construct our score, we identified 5 factors that we found to be correlated with an adoption of electric trucking infrastructure. First, the environmental friendliness of a region. This was found by polling data on opinions about carbon emissions from each of the states. Second, the net decrease in carbon emissions resulting from the adoption of electric trucking along each corridor. Third, the average of states' relative budgets allocated towards highway development in each region. Fourth, the initial cost of installing the necessary number of stations and chargers calculated in Part 2 along the length of each corridor. Fifth, the operational costs of electric trucking in each region, based on the average cost of electricity in each state. Using a normalizing technique known as featured scaling, we added or subtracted each of the factors based on whether they were predictive of a region installing electric trucking infrastructure or not. For example, the more environmentally friendly a region is, the more likely they would make the move towards electric trucking. However, the greater a region's cost to install such infrastructure, the less likely they would be able to make that change. Therefore, the greater a corridor's score was, the more likely electric trucking infrastructure would be installed along it. Now, Danny will talk about our interpretation of the results.
As we progress into section 3.4, the equation allowing us to arrive at a total benefit score is represented with a value for local opinion plus the miles plus the budget minus the operational cost minus the initial cost. We noted that the pathway from Minnesota to Chicago had the best score. We believe that this could be attributed to the fact that the states contained within this corridor had the greatest budget to make these changes to their infrastructure and one of the lowest initial costs to build charging stations. Moving into section 3.5, our sensitivity analysis hinges on the fact that the normalized values of all of the variables except one are already based on averages of well-established data sets. As Vinay explained previously, the benefit score we are looking at normalized the variables in the same fashion. However, we could not find analogous data involving relative costs of building new stations along each corridor. Thus, we studied a cost variable that is given as a weighted average of the normalized cost to building chargers and a normalized cost associated with building charging stations. We computed these benefit scores under a variety of different weightings, and our results are shown in figure 4. We noted that all of the corridors except corridor 2 are almost completely invariant under a change of weighting. But even in the case of corridor 2, the effects do not change the relative rankings of our benefit score. Therefore, we are confident in our decision to average the cost of the chargers and charging stations, seeing as it will not affect a ranked prediction in our conclusion. Finally, section 3.6, our model is strong because its structure allows for the introduction of other factors with little or no difficulty, making it robust and highly adaptable. However, our model is weak due to our arbitrary weightings of the variables. In the future, we could study the introduction of relative rates between factors, thus placing emphasis on specific factors to be determined by additional data. We could introduce these weightings with little difficulty because our benefit score allows for simple modification. We could further model the sensitivity analysis with modified parameters using the techniques we used to study the invariance of the relative costs of charging stations and chargers. In conclusion, our preliminary analysis used a Monte Carlo simulation to predict the number of long-haul and regional-haul electric trucks that would be in operation in the next 5, 10, and 20 years. Assuming a mean range per charge, we were also able to determine an optimal number of charging stations as well as an optimal number of chargers per station along major interstate routes. Finally, we assessed the value associated to placing charging stations on several different corridors using a benefit score whose parameters were fixed using available data. We completed a sensitivity analysis for one of the variables, which serves as a model for what can be done to establish the stability of our results under small changes in the data. Our findings lead us to encourage Americans to embrace the movement towards a more sustainable future that involves electric trucking.
We just want to take a minute to extend a quick thank you. This is 3 of our second and final year participating in the MathWorks Math Modeling Challenge. And this challenge, I'm going to speak for all of us, saying it's been not only extremely fun, but extremely beneficial and impactful for our futures. So thank you to our wonderfully supportive coach, Mark Mattia, the coach before him who brought the MathWorks Math Modeling Challenge to Pine View School, Chris DeVoe, some of our excellent Pine View faculty who have supported us always, to name a few, our principal, Dr. Stephen Covert, and vice principal, Tara Spielman. Additionally, we want to thank Professor and Mrs. McDonald for always helping us out and for getting us pizza after every practice and mock. Also, we wanted to thank the New College of Florida for providing us with a great meeting room that we were able to conduct the challenge in. And finally, a huge thank you to Simon Mathworth for holding this challenge.